Yes, sir.
Okay. Okay, you can complete.
Start.
So recording is started.
In this case, somebody thinks that they should put some white chalks here.
Okay, okay.
Because this color chalk doesn't show in the board, it's screen color. No? So,
Only 10 students are there.
huh?
Only 10 students are there. I don't know.
On hold, why somebody is on hold?
Hey, he has not joined.
That's
He got the this thing.
only why are they, yesterday they were about 19 or something. No? That means apart
Maybe
from me, there
tomorrow
are
the
9
exam
exam
maybe.
is there. I think that's why.
But that should not.
But then they should tell you know, that you don't want to the class.
Anyway. Okay.
Okay, can you hear me?
Yes, ma'am, but you are not visible.
That's okay, as long as you can hear me and as long as you can see the board. You people are also not visible. It makes it even if I'm not visible. Yeah. So yesterday what I was discussing was that what are the various operations we can do with tensors. So essentially I was discussing the algebra like addition, multiplication, and so on. And so we saw that we can add tensors of the rank of the same rank, and we will get again another tensor of the same rank. Similarly, I can subtract and get a tensor of the same rank. Then we can also discuss or define what is known as the outer product. So if I take the outer product of a tensor of rank m with that of a tensor of rank n, then I'm going to get a resultant object which will transform like a tensor of rank n plus n. And then I said that. So the outer product essentially what it does is that you're taking you're sort of combining two tensors of rank m and n, and then you're getting the resultant which is of a higher rank than your constituent tensors.
Excuse me, ma'am.
Yes. Yes.
Ma'am, your video is not on, so we cannot see the blackboard as well as anything.
Blackboard also you can't see, is it? So let me just just 1 minute. Wait, just hold on. Okay? I'll just come. something, so it is come now. So we include that. Okay. Okay.
खड़ू लागने लगे है ना खड़ू
हाँ चौक दे दो इधर ना सफेद चौक पूरा दे दो
थोड़ा देगा
सफेद चौक ही लेबल करो हाँ खाली कलर चौक ना करते
Now you are able to see the board.
Yes, sir.
Okay, thank you. What did you do?
तो कैमरा ब्राउज करना
Okay, I hope now things are settled. So let's go back to what I was doing. So as I said last time, at the end of the thing, I talked of something called a contraction process or a contraction of tensors. So first I'll talk of contraction of one tensor. So let's again I'll go back to the example I started with. So if I have a second rank tensor, Dij, so it's varied by two subscripts I and j, where I takes values from 1 to 3 and j also takes values 1. And if I now consider this object, Dii, so basically what I've done is I've equalized these two subscripts. So I and j have become the same. And then because of our summation convention, what this means is I'm summing up over this subscript I. So what this represents actually is I equal to 1, 2, 3 Tii. Or, so I write it. Maybe this becomes a little bit more. Okay. So this really means T11 plus T22 plus T2. So I again want to emphasize, what we've done is we've taken the two subscripts of your tensor, equalized them and summed them. And this, as you can see, is because this is nothing but this matrix T11, T12, T13. This is for a second rank tensor. So this is nothing but trace of the matrix tensor. Then what we asked is the question that how does this quantity transform under your notations? Now by definition you know that Tij prime equal to Rij, Rik, Rjl, Tp. So this is the transformation property, the second matrix. So if I want to have the transformation, okay, now this you can see, I can also write it in the following way. I can write this as Tij delta. This is another way to write the same. Because your delta, the Kronecker delta is defined as that it's equal to 1 if I and j are the same, and it is 0 otherwise. So therefore this is going to sum up like this. So therefore I can write my Tii prime as equal to Tij prime. Or let me do it directly. So if I have T11 prime plus T22 prime, so I'm going to do directly from here, T33 prime. Then this is equal to R11 or R1L. Okay, by definition. And this is nothing but, so your Pi prime equal to this by definition. And this is therefore equal to R1L, R1N plus R2L, R2N plus R3L, R3N. here. But what is this? This is nothing but RIN. Because this is by definition, you can see that this summation, it's the first indices are being summed. So I just put the same first indices again by a summation convention. This means you're summing up the R. But what does this give me? Now, using the fact that the rotation matrix satisfies R transpose equal to identity equal to R transpose R. This is like as if you're doing R transpose. So this is like R transpose Li, RIN, CSM. But R transpose, so it's like as if you multiplied R transpose with R. But we know that R transpose R is nothing but identity matrix. So therefore, this is going to give me simply delta Ln, Ln, which is nothing but. Or in other words, this is exactly what I did yesterday. So T prime II is the same as TLN, and now this is a dummy index. I could as well write here TIN. See, this kind of index manipulation or playing with indices is something which you have to learn. It comes with experience. But I'm just using this so that you can see that we can manipulate indices and get equal. So anyway, what I've shown you therefore is that T prime II is the same as TIN. Or in other words, that trace T is the same as trace T prime. Or trace T with respect to basis P is the same as the trace of the matrix with respect to the basis P prime. Or in other words, this quantity transforms like a scalar. So although you had this T transforming like a second rank tensor, once I contracted this, okay, so this process of equalizing two indices and then summing over them, this is called as a contraction. And in the process of contraction of this second rank tensor, I ended up with an object which transforms now like a scalar or a tensor of rank 0. So that means I've reduced the rank of the tensor by 2. So now I can generalize this to any higher order tensor or a higher rank tensor in the following. So suppose I have I1, I2, I3, In. So this is a tensor of rank m. And now what I will do is I will contract, say, okay, so let's write some two indices here or two subscripts. So let's say I have Ik, then Il, and this is In. So this is a tensor of rank n. And now let me say I contract in the indices Ik and Il. So I will have therefore then I1, I2, I3. So contracting in this means Ik and Il become the same. So it becomes Ik, Ik. Then I have In. Okay. Now this object, where you're equalized the two subscripts of Ik and Il, and then because of the summation convention you've summed over. Now what you can show is that this is going to transform like a tensor of rank n minus. And it's easy to do, you just follow whatever I've done just now. So take the prime of this and show using the properties of your rotation matrices. So the only thing which you're using is R transpose is equal to identity equal to R transpose R. That's all you use. Okay. So verify this. Okay. This is an exercise that you can do. Yes. Yeah. Somebody was asking something. Okay. It is very straightforward to do this. So all you need to do is write this in the following way. I will just tell you what to do. And, I mean, all of you have said that you will do it after the exam. So I hope that at least we'll try it out, we will do them. So what we do is, the idea is that you construct, take this object, ik, m, im. So write this as sigma ik equal to 1. Explicitly write this in terms of the tensors. And then after that, use the relation between how a tensor of rank n transforms. So that many, you have to put this many r. So that means you have to put m number of r's. Okay. And then, as I said, the only thing you need to use is that r transpose r is equal to I. So you will get some Kronecker deltas. Using that, you can show this idea. But now you can see that we have, okay, so what we have therefore seen is that I can multiply two tensors. 4. So if I multiply a rank m tensor with tensor of rank m, this produces a tensor of rank m plus. And then I can do now a contracted tensor of rank m in two indices or in two subscripts. Okay, so I will write it as two subscripts. So with respect to, I will write with respect to two subscripts, then I will get a tensor of rank. So it just produces a tensor of rank m minus 2. Right? So suppose I start with a tensor of rank 4. Then I can contract it with respect to two subscripts. I will get a rank 2 tensor. Now that rank 2 tensor I can further contract again in the two indices and finally end up with now a rank 0 or a scalar. So it's possible therefore now that given a rank m tensor, I can contract in more than two indices. So from a 4th rank tensor, I can first contract in two indices, then the next two indices come to 0. From a 6th rank tensor, I can do with 2 first, come to a 4th rank tensor, then from 4th rank, I can come to a 2nd rank tensor, and then finally to a scalar. This is a very important thing which we will be using a lot, both this contraction and multiplication. And I'll just show you another nice, neat way of thinking of contraction. See, we already saw that if I have u and v as two vectors, then I can construct this object eij as equal to ui vj. Right? This is something which we have seen, that, or this is nothing but the outer product of two vectors, and which is the same. Now the contraction process is TII, so this means it is equal to UI VI. But what is UI VI? So for this particular example, what is UI VI? If given two vectors, what is the meaning of this expression UI?
Inner product of u and v.
The inner product. And you know that the inner product transforms like a scalar. So if I define therefore the outer product of two vectors and produced a second rank tensor, then the trace of that second rank tensor is nothing but the inner product of those two vectors. And you know that this you already know that the inner product is a scalar, and we have already demonstrated now that the trace of a matrix is a scalar. So I've talked about adding, subtracting, multiplying in quotes, contracting. Then there's also something, you can ask whether I can do division of tensors. Well, you can't explicitly divide A by B to tensors, but we can talk of something called a quotient law, but I think I will postpone that for a little later. maybe I will just delete it perhaps. Or okay, I'm going to postpone this when we actually do examples at analytical finance. Or when we do exercises, then I will show it, because I think even if I say it now, it won't be very useful. Instead, now what I'm going to ask is, I'm going to now construct some or consider some special tensors which, see, we're talking of this quantity delta ij, the Kronecker delta. So this is defined as 1 if I equal to j, and this is equal to 0 if I not. Now this is a set of 9 objects. So your delta is, the matrix is this. Simply the identity matrix, nothing more than that. Now the question I can ask is this a tensor or not? Is this object a tensor or not? Now, automatically from looking at the subscripts, or because it has 9 components, you should imagine that if at all is a tensor, it can only be a second rank tensor. Right? So the question then is that, can we demonstrate or can we check or verify that or find out whether it's a tensor or not a tensor? Now by definition, because delta ij is this, in any other basis, so this is supposed with respect to basis B, now with respect to basis B prime also, because of the definition, it is simply the same. This is by definition, okay? Because it's how I have defined it. Or in other words, the components of delta do not depend upon which coordinate basis you are using. Again, I want to emphasize we are talking of B and B prime related only by rotated coordinates, rotation transformations. And also, I'm only considering right now. I also want to remind you that I'm considering rotation transformations where determinant of R is +1. So from here you can see that this set of 9 elements do not depend upon which or how you are actually choosing the coordinate axis, and they don't therefore depend upon x, y, z for the components. So now I want to demonstrate or tell you that this is really a second rank tensor. So how do I do that? By definition, a second rank tensor must have this transformation property that P prime ij should be equal to Rik Rjn Pk. So if I can show you that delta and B prime is related to delta and B by this relation, so instead of P here I put delta here, then in that case I'm done. Right? So let's consider the right hand side of this expression and I replace this P by delta. Consider Rik Rjn delta. So consider this. So here now the summation indices are K and N. Now according to this expression and from the definition of your delta, Kronecker delta, this expression will be 0 unless K equal to N. So what this tells me is that variable I should replace it with K. So this is the same as Rik Rj. See, it's just like when I write AI, suppose I have AI into delta Ij, then this is nothing but Aj. Because this tells me that, or the definition of your delta tells me that this is going to be 0 unless I equal to J. So wherever I comes, that is equal to J. But what is Rik into Rjk? This you can see is nothing but Rjk. I can write it as Rik into R transpose of Kj. Because the Rjk element of R is nothing but the Kjth element of R transpose. And this, if you look at its multiplication, this is R transpose Ijth element. But what is R transpose? This is nothing but the identity matrix And the ith element of identity matrix is nothing but delta I. So what we find therefore is that if I define delta prime ij as equal to this, then this delta prime ij is the same as delta ij. So first of all, I find that so what this tells me then is that my delta transforms, because this exactly is satisfying my definition. Because I find that delta prime ij, because you can see here delta with respect to b and delta with respect to b prime are the same, and it satisfies really my transformation property of the second rank tensor. So therefore, what we've shown is then that my delta transforms like a second rank tensor. So this Kronecker delta, delta ij is a special tensor. It's a second rank tensor. And as you can see, why do I call it special? It is special because the components do not depend at all on which coordinate basis you're using. They are independent of the coordinate basis. And we'll see later that such a tensor is called an isotropic tensor. So where you have a tensor like this, which is independent of the coordinate system, or in other words, it's not depending on how you're orienting, because we are talking about your rotation transformations. What it tells me is that it doesn't depend upon how I'm orienting my coordinate axis. It doesn't matter, because these values are independent of that. So therefore we call it as an invariant tensor or an isotropic. Isotropic means it doesn't matter in which direction I'm looking at the tensor. I'll come back to that. So this is really an example of what is called as an isotropic tensor. So it's sometimes it's called an isotropic or an invariant tensor. So this is one special tensor which we will be particularly interested in. And now I can show you that it's very useful to have this tensor, because consider this object. Suppose I have two vectors, u and v. So let's say that I have two tensors of rank 1, and I consider this object ui vj. So aij I have defined. This is now I know that it's a tensor of rank 2. And if I now consider ui vj delta ij, what will this be? So I have ui vj delta ij, which is nothing but aij delta ij. What is this equal? This is by definition. What will this simplify? See, what does this tell me? This tells me that this expression is zeros. Okay, maybe I think what you should do is, I'll do this for once, but later on I think you can see this. See, what is the right hand side A and B? Here both I and j take values 1, 2, 3. So it tells me that u1, and whenever we have, now you can see in this expression I have two summation indices. One is the I summation index and the other is the j summation index. Whenever I have such two summation indices, or when two indices are being summed over, then in that case what you do is keep one of them, don't, so for example here, don't do anything to the j, just expand in terms of the I index first. So you write it as u1 vj delta 1j plus u2 vj delta 2j plus u3 vj delta 3j. Fine. So this is by definition. So I still then have to do a summation over the j index. Now when I do the summation over the j index, j can take values 1, 2, 3. But once I fix a first index of delta here as 1, what is the only non-zero value which I can take for j? Or what is the only value for j which I can keep in such a way that this gives me a non-zero answer? See, each of this means, so again, the reason I'm doing this so elaborately is because we're using such expressions very often. So I have u1 bj delta 1j. So by definition, this is going to be u1 v1 delta 11 plus u1 v2 delta 12 plus u1 v3 delta 13. Agreed? Now, what answer will this give me? What is delta 12 value?
Zero.
0. So 0 multiplied by whatever this is going to give me 0. Because after all, it's going to be 0 multiplied by something. What about this term? Again, here I have delta 13. So what is the value of delta 13?
Zero.
0. So 0 multiplied by u1 v3 will again give me a 0. So this term goes identically to 0. This term goes identically to 0. And that's simply because your delta 12 and delta 13 are 0. So finally, I'm going to get just this. But what is delta 11? 1. Because you see, I and j are the same. Then in that case, it takes value 1. So I'm going to simply get u1. Or in other words, you can see that when I have u1 bj delta 1j, the only non-zero answer I will get is when I put the j to be the same as the first index. That is 1. That is because of this definition of your delta tensor. So if I put j equal to 1, then this automatically becomes 1. So I will simply get only u1 v1. The other two terms get killed because of this delta. So from this first expression, I'll simply get u1 v1. What about this one now? u2 vj delta 2j. From this, what will I get?
U2 V2.
I can only get u2 v2 because delta 2j, once this is fixed to be 2, then j can only non-zero answer will come when j equal to 2. So this gives me simply u2 v2. And finally, the last one.
U3 V3.
And what is this? u1 v1 plus u2 v2 plus u. Just a second. Or what is u1 v1 plus u2 v2 plus u3 v3?
Inner product.
Yeah, but in compact notation,
Trace.
yeah, it's a trace of this, but in terms of just the use of compact, there's nothing but ui vi. Because you're summing over I index now, I equal to 1. Is this correct? All of you agree with this? See this last one, u1 v1 plus u2 v2 plus u3 v3. I can simply write it as ui vi because this is summation over the I index, repeated summation. So therefore, what we find from here is that Tij delta ij, okay, and this is nothing but your trace, or this is nothing but your Tii, by definition from here. So Tij delta ij is nothing but Ti. Now your right hand side is something which I call as a contraction of my second rank tensor. So what I can do therefore is multiply Tij with delta ij, and that leads to a contraction. Because delta ij is to be, because any other combination if I get, it will just cancel it because of the fact that if I and j are not the same, that will become 0 here because of the delta. And once I force these two to be equal, then because of the repeated summation, you're summing over the equal indices. Or in other words, what I'm trying to say is that I can use my delta ij to contract indices in any tensor. So I can write my, so if I have, let me now write it. Suppose I have T, I1, I2, say IK, IL, and IM. Multiply this with delta IK, IM. This is like multiplying a tensor of rank n with the second rank tensor. Because I've already demonstrated for you, delta is the second rank tensor. But what this does is, I will now get this as, because IK should be the same, I1, I2 like this, so it will become IK, IK, IM. So basically this essentially becomes now n minus 2 times. So this is something which is interesting, but if I multiply with this delta tensor, because of the fact of its peculiar properties, instead of getting an n plus 12th rank tensor, I will actually get an n minus 12th rank tensor. Indices or the contraction of a tensor with respect to two indices can be achieved by taking this tensor and multiplying it with this, or combining it with the delta tensor. And I've also given you this example that if I take AI delta IJ, then this is going to give me an AG. Because again here, this will be 0 unless I equal to J, so I will end up with this. In this case, I'm going to end up with, see now notice that I'm going to, so here what this left hand side means is this. A1 delta 1, 1. So if J, suppose you're, okay, let's say. What is J here? J is the free index here. Whereas I is a summation index. So when it's a free index, I put J equal to 1, suppose. Okay, so let J equal to 1. Then what this means is A11, so A1 delta 1, 1 plus A2 delta 1, 2 plus A3 delta 1. So I summed over this. See, J is free, so I have to fix the value of J, which is 1. And finally, I'll get from here A2. So, or in other words, by doing this from the vector A1, A2, A3, I pulled out the third. In this case, I pulled out the first one. Because delta 21 is 0, delta 31 is 0, so I pulled out the first one. That's what this is doing. So, if I want to extract out a particular component from some vector, or even say a particular component from a tensor, again, I can do that by using suitably the delta tensor. We'll see more of this when we deal with examples later on. Okay. All right, so that's some, as I said, this is, and what we will find is that it's also very useful when we do our usual vector algebra. And again, as I said, I'll demonstrate that when we do examples. Another tensor which we are going to be, another object which we are going to be very much interested in is the following. Consider this is something which will be familiar, but again I will present it. The Levi-Civita, I'll first call it simply a symbol. Okay, epsilon I. Now, I can take values 1, 2, 3, J can take values 1, 2, 3, K can take values 1, 2, 3. So, how many components are there in this object altogether? It has 3 subscripts, I, J, K, and I can take values from 1, 2, 3. J can also take values from 1, 2, 3. So, how many altogether? How many components are there for this object? Pardon? How many?
27.
Yeah. I asked how many components are there in this object? You have 3 subscripts, so how many components? So one of you have said 27, which is correct because this can take 3 values, this can take 3 values, this can take 3 values. So 3 into 3 into 3, 27 values. And now I define it in the following way. But this is equal to +1 if ijk is an even permutation of one, two. Okay. So this is by definition -1 if ijk is an odd permutation. I'll tell you what we mean by even and odd permutation of this in just a minute. And this is equal to 0 otherwise. So what this means is by definition. So I have these indices 1, 2, 3. So if ijk here is an even permutation of 1, 2, 3. So if I have 1, 2, 3, I can permute these numbers. So one positive permutation of 1, 2, 3 is that I exchange these two. So this will be like say 2, 1. Right? So that's one permutation. Then I can do another exchange. So I do this now, P, 1, 2, 3. So I exchange these two. Or let's say I exchange this one. So I get 2, 3, 1. So I started from here, and to go to this, I needed two permutations. Because I first exchanged 2 and 1, then afterwards I exchanged 3 and 1. So going from here to here consists of, or in other words, this particular order of these numbers 1, 2, 3 can be achieved from here by doing two permutations. On the other hand, this particular order of the three numbers 1, 2, 3 can be achieved from here by doing only one permutation. So this I will say corresponds to an odd permutation of 1, 2, 3, and this I will say corresponds to an even permutation of 1, 2, 3. Okay? And what this definition is telling you is that if your ijk is an even permutation of 1, 2, 3, then the value is +1 for this epsilon. And if it is an odd permutation of 1, 2, 3, it is -1. And otherwise it is 0. So what this immediately tells me is therefore that if my epsilon had taken value like this, then what will be the value for this? From this definition?
0.
0.
0.
Because obviously I cannot achieve 1, 1, 2 by doing anything to 1, 2, 3. Or in other words, what this tells me is that from this definition, the non-zero values of this Levi-Civita symbol are only when ijk are all different. If any of the two indices are the same, then the value is identically equal to 0. That's what this definition tells us. So all these two subscripts must be different. So I can get epsilon 1, 2, 3. So non-zero answers can come only for this 2, 1, 3. Now given three numbers, how many different permutations can I get?
3 factorial.
So the 3 factorial is how many?
6.
6. So which means only for these 6 values, you write down all this. Epsilon 2, 1, 3, then 2, 3, 1. What are the others? 3, 1, 2. Epsilon 3, 2, 1. And then what is the final one? Epsilon 1, 3. Right? Yeah, that's right. So these are the only epsilons for which the answer is non-zero. Okay. Now this corresponds to something with which I have not done any permutation, so this value is equal to +1. What about this? What will be the value for this quantity epsilon 2, 1, 3?
-1.
-1. What about this one? 2, 3, 1?
+1.
Yeah, this is going to be +1 because see, I'm going to do this from here by doing two permutations. What about this one? 3, 1, 2? What about this one? 3, 1, 2? How to achieve 3, 1, 2 from here? 1, 2, 3. One way is that you just take this, change this, so I get
+1.
So it will be equal to +1, obviously. Then this one?
-1.
-1. About this one, people?
-1.
-1.
Great. So these are the only, so you had 27 components. Now out of the 27 components, 21 are actually zero value because of this definition, and only 6 of them have non-zero values. And again, you can see that this particular object has values which doesn't depend upon your coordinate system. That means if I define it in some other basis, so this is, I define it with respect to some other basis, because it did not depend upon whether I chose x, y, z or E1, E2, E3 as my basis, or E1 prime, E2 prime, and E3 prime as my basis. This is independent of that. It's just depending upon the subscripts. So this definition is independent of the basis. Fine. So now again, I want to claim now that this particular object, epsilon ijk, is a tensor of rank. So this is my claim. And how do I prove this? That it's a tensor of rank 3. So again, I will show you this. I can't now use a matrix form because it's up for these 3 subscripts. But again, I want to emphasize that epsilon prime also has the same definition because your values don't depend upon which coordinate system or how I'm using my basis. But if I can show that, so if I can verify that epsilon prime ijk equal to ri l rjn rkn epsilon ln. If I can show this, if we can show this, then we are done. Because then it tells me that the transformation properties of this object are like that of a third rank tensor. Notice that in here, in this, I know what is epsilon ln. I also know what is epsilon prime ijk. But I have to show that the relation between epsilon prime ijk and epsilon ln is this. Now, before I go there, I just, if I want to demonstrate this, I just give you a little bit of something which you already know. This epsilon is something which you probably have encountered earlier. And it's not something which is completely new. Maybe I will just show you some identities. It is useful. Consider a 3 by 3 matrix. Suppose I have a matrix A. Okay. So I want to show this, but in this process, I'm going to show you something else. So let's say I have a matrix A and its elements are given like this. Okay. Now, how is it? What is the determinant of it? Let's write it explicitly. What is the determinant of it? We have a 3 by 3 matrix. How is the determinant? Yeah, let's do it explicitly. There's nothing, I would like to do it explicitly for once. Yeah. How would you find out the determinant? I think you do this in school. You write A11 into, what do you call that the object? Is anybody there or not there, or everybody has gone?
A22 into A33 minus
What?
A2.
A1? Yeah, so we write this into the cofactor of this, and the cofactor of this is this determinant, right? So I'll write it like this: C11 plus A12 into C12 plus A13 into C1. Where the C11 will be this, and C12 will be, to remove this, you will get the determinant of this. And so finally, what will I get? So the Cij's are the cofactors. And this is going to give me A11. So determinant of this will be A22, A33 minus of this. So I'll get A22, A33 minus of A23, A33 from the first term. Then I have A12, and now when I take the cofactor, I remove this row and this column. Sorry, this column and this row. So I get the determinant of this. And you have to take the sign also when I take into account. So it's 1 plus 2, so I take a minus sign. And I'm going to get A21, A33 minus of A33, A31 plus finally I will get A13 into A31, A33. So everybody agrees with me that this is the determinant of your matrix A. What you can see is that, okay, now our the use of our compact notation. So I have here, you can see A11, A22, A33. Then I have minus of A11, A23, A32. Here minus A12. Okay, so if you look at this, in all of them, the first, if you look at the first index, you have 3 A's in each term, right? And if you look at the first one, I have 1 here, 2 here, 3 here. The next one I have 1, 2, 3. The first index. Then I have 1, 2, 3. Again 1, 2, 3, 1, 2, 3, 1, 2, 3. So I can write this in this compact way as equal to. Okay, I'll just write it down and then you will see this. So forget for the minute whether this is a tensor or not, but this epsilon is very useful object because I can write my determinant now in the very well. Yeah. I'm sure that some of you are familiar with this. Some of you may not be that familiar. But see, our repeated summation convention and all these objects which we are introducing, it's hard to remember this kind of things. Or it's clumsy to remember it, but on the other hand, this is a really neat expression and very useful to remember. And you can see that once I do in this fashion, once I write it like this, the signs are also automatically taken care of. Because you see 1, 2, 3, then I have here I, J, K. And epsilon I, J, K we saw was already that this object is 0 unless each of the, these I, J, K must be different. If any of the 2 indices are repeated, in that case, it gives me a 0 answer. Okay. So it means that IJK must take values of 1, 2, 3. Suppose it takes 1, 2, 3. Then in that case, I'm going to get epsilon 1, 2, 3 here. I'll get a plus 1. So I get this first time. But suppose it takes values 2, 1, 3. That means 1, 2, 2, 1, 3, 3. In that case, I'm going to get a minus. This because it will become minus A12, A21, A2. So automatically the signs are taken care of and this whole expression becomes very neat. Okay, so the determinant of, okay, generalize this to higher orders also, but let me just do this. So for a 3 by 3 matrix, I can write my determinant of A lines. But you can also see that I can play with this a little bit. Now, what we have also seen is that suppose I have epsilon ijk from the definition. How is epsilon? Is there any relation between epsilon jik and epsilon ijk? Okay, maybe I can do it like this. Epsilon 1, 2, 3 equal to plus 1. Epsilon 2, 1, 3, what is the value of this?
Minus 1.
Minus 1. So this is like minus of epsilon 1, 2, 3. Agreed? Because epsilon 1, 2, 3 was plus 1, whereas epsilon 2, 1, 3 is like minus of epsilon 1, 2. Or in other words, if I exchange these two indices, then I'm changing the sign. And you can see now that if I have, okay, 1, 1, 2, what will be the value of this?
0.
0. Okay. And if you go further and look at the definition again, what you will find is that, I mean, if you look at this a little bit more elaborately, you will see that your epsilon ijk equal to minus of epsilon gi. That it satisfies this condition. That means if I exchange the first two indices, for example, so if I take ij and then change that, replace this with ji, then I will get a minus. If this is consistent. For example, I put here 1, 2, then I put it as 2, 1, I'll get a minus sign. Similarly, if I put here 1, 3, 2, and I change it, I'll get again a minus sign. And this is also consistent with that. Because, for example, if this tells me that if the two indices are the same, so this tells me, for example, that epsilon 1, 1, 2 should be equal to minus of epsilon 1, 1, 2. So I've changed the indices, but 1, 1, if I change, I should get back the same. And this immediately tells me that epsilon 1, 1, 2 is equal to 0. And in fact, what you can see from the definition is that it's not just an epsilon is not just antisymmetric under exchange of the first two indices, it is antisymmetric under exchange of any two indices. So this is actually is an object which is completely antisymmetric under exchange of any two indices. Fine. So using this now, I'll just take another 2 minutes. What you can see is that, okay, this is what I mean by saying that we play with the indices. So what I'm going to do is, instead of, after all these are dummy indices, now which I call, because I'm summing over I, I'm summing over j, and I'm summing over k. So I could have easily written this as a1j, a2i, a3k, epsilon ji. It doesn't matter because I'm finally going to sum up all these. But then I use the fact that epsilon gik is nothing but minus epsilon. So I write this as minus a1j, a2i, a3k, epsilon I. So notice what I've done here. When I went from here to here, this part remained the same, but I exchanged this here and I got an extra minus sign. So this has now become like minus a2i. So I can think about it like this: a2i, a1j, a3k, epsilon I. Okay, we'll continue with this, playing around with this a little bit again. So I'll stop here. We'll continue, I think, on Wednesday next. Or maybe I'll just take one expression to you. You can just verify this expression. Maybe that's what I was trying to make you. So I'll just stop with that. So what I want you to show is using this identity and playing with this a little bit, just verify the following. That epsilon LMN determinant of A will be equal to AMI, AMJ, AMP, epsilon IJ. And A here LMN takes values 1. So verify this. So you just have to take this, whatever I've been playing with this, and then try to see if you can do that. But it's only 12:25. Your class is supposed to start at 12:30. No, according to this, it's 12:25.
Yeah, 12:25.
But how do I stop this? Okay, first of all, I should mute.